Good morning, all of you. Am I audible?
Yes, sir.
Okay, thank you. So today we would be continue the unit number 5 that we have started in the last lecture. So we have started with the passband technique of modulation, that is amplitude shift keying. So we have learned in the last lecture about the generation and detection of the ASK, as well as we have gone through some mathematical equations to represent the amplitude shift keying technique, and we have seen the uh, signal space diagram of the ASK as well. And at the end, we have ended our lecture on a point that there are two types of the demodulation technique in the ASK. One is the coherent, another is the non-coherent. So we have seen the coherent detection already. So today we would be discuss about the bandwidth of the ASK. So if you have to be talk about the bandwidth of the ASK, the bandwidth of the signal is basically what? It is a total range of frequency occupied by the signal. And when we decompose the ASK signal, we get a spectrum of some simple frequencies, and the signal at the center of this spectrum can be referred as a carrier signal, that is F0, and at the either side are the signals with the frequency, that is F0 minus n baud upon 2. N baud is the baud rate, or F0 plus n baud upon 2. Like this, the odd and even components of the this frequency would be there: F0 minus 3 n baud by 2, F0 plus 3 baud by 2, and so on. But for the practical purpose, uh, however, only one carrier frequency and two closest side frequencies are required. In this diagram, you can note it down this diagram or take the screenshot. Here we have to be see that there is an amplitude versus frequency curve is there, and in this case, if you have to be see, uh, the bandwidth of the ASK has been be defined as the formula bandwidth BW is equal to 1 plus D n baud. So here BW is bandwidth, n baud is a baud rate or symbol rate you can say, and D is the factor related to the filter characteristics, and its value would be lies between 0 to 1. Minimum value is 0 and maximum you can take it as a 1, or in between of that there is a value would be lies. And if you have to be see the diagram also, you have to be find that the minimum bandwidth of the ASK is equal to the baud rate. Means minimum bandwidth of the ASK would be equal to n baud. And the center frequency has also shown F0, and the two side frequency F0 minus n baud by 2 and F0 plus n baud by 2 has been shown. So this is the frequency response of the ASK signal, or this is the very important formula for the bandwidth 1 plus D n baud. Now we have to be see the last topic on this ASK, that non-coherent detection of ASK signals. So you can see the block diagram here that would be representing the non-coherent detection. So what is the difference between the coherent and non-coherent detection? So we have to be see the only difference is that in the non-coherent detection, the carrier signal which is using at the transmitter and the receiver side are not in same phase with each other. In the case of synchronous or coherent detection, both are in phase. Okay, but in this case, non-coherent detection, it is not in phase. By this reason, this detection is called as the asynchronous ASK detection. And this demodulation process can be completed with the help of the following devices, like the square law device is there, then the low pass filter, or you can also use the band pass filter if it is a band limited signal, then comparator and voltage limiter. So generally, whatever the ASK signal has been transmitted from the transmitter end, when it would be passed through the channel, there is some noise and the errors would be added, and this noisy signal would be received by the receiver, and the first it would be passed through the square law detector, where whatever the carrier signal cos omega naught t or cos 2 pi f naught t would be, it would be squared, and there is a second frequency component would be generated. It would be passed through the uh, twice of f naught, it would be generated actually, and it would be passed through the low pass filter, that is band limit, that is having the bandwidth that is equal to the bandwidth of the transmitted signal. So it would be remove the DC components and other unwanted frequency components, and then finally output of the low pass filter, you can say it is some binary signals would be there, that would be the two voltage level actually, and that would be passed through the comparator, and the output of the comparator, the signal uh, having the binary value, or that would be as the same as the transmitted signal. If there would be any change in the amplitude of the signal, that could be limited by the use of the circuit voltage limiter. And finally, we would be receive a demodulated binary pattern or binary signal is there. So this is all about the non-coherent ASK detection. Okay. So if you have to be talk about the applications of the ASK, that is a lots of applications of ASKs are there. Low frequency RF applications in home automation devices, we have to use the ASK, as well as the industrial network devices, wireless base stations, and one of the very general application is tire pressuring monitoring system. Also, you can use the ASK. Now we have to be moved to the next modulation technique, that is binary phase shift keying, BPSK. So BPSK is a simple but significant carrier modulation scheme. In the BPSK, if you have to see, the transmitted signal is a sinusoid of fixed amplitude. Only the phase of the carrier is varied between the two states to represent the zeros and ones. And the pair of the signals S1T and S2T is here, used to represent the symbol 1 and symbol 0 respectively. Means S1 would be represent the symbol 1 and S2 would be represent the symbol 0. And mathematically you can write it as S1T is equal to square root of twice of PS cos 2 pi f naught t, where square root of twice of PS would be the amplitude of the signal. Actually, we have learned in the last lecture how this amplitude AM would be converted into the in terms of power form. So I'm not going to discuss again and again. So this square root of twice of PS is nothing but the amplitude of the signal, and this S1T is a representation of the binary 1. Okay, so if you have to be see the representation of the binary 0, as we have seen that we have changed the phase of the carrier with respect to the incoming signal. So here the S2 would be represent the symbol 0. So S2 would be represented as a square root of twice of PS cos 2 pi f naught t plus y. So it is you can say it is a 180 degree out of phase with respect to the symbol 1. So you can also say it as minus square root of twice of PS cos 2 pi f naught t. So in this way, both the symbols 1 and 0 would be represented differently because of there is some phase difference of 180 degree, and both are out of phase signals are there. Then further, if you have to be going to combine this S1T and S2T, you can give the equations as well. If you want to give the number of equations, you can put up this. It is not mandatory, but for simplification you can do this. So when you have to combine the equation 1 and 2, you would be got the equation for the ST That is the composite value of the signal here. So st is equal to here bt square root of twice of ps cos 2 pi f naught t. So what is the bt is here? Bt is nothing but a baseband signal. So this baseband signal is actually a non-return to zero polar signal, NRZ polar signal, having the amplitude of plus 1 volt and minus 1 volt for the logic 1 and logic 0 respectively. Therefore, you can also write it as st is equal to plus minus square root of twice of ps cos 2 pi f naught t. So either you can represent this uh, PSK signal as through the equation number 3 or equation number 4. It doesn't matter because both are the same, only the way of representation is changed. Here we have used the plus minus in the equation number 4, and there we have used the one symbol, that is BT, that is NRZ polar signal. Okay. So if you have to be represent through the diagram or the waveform of this binary phase shift king, so the idea would be more clear that how the 180 degree out of phase signals are generated. So you can see here, this is the 4 waveforms has been shown in this diagram. The first one is representing the binary data, that is in the form of the 1 and 0 only, and it is a unipolar signal actually. But in the second case, you have to be see it is a bipolar NRZ. It is a bipolar NRZ signal. So according to the value of the binary numbers or symbols, it would be its value of the voltage would be changed. So for the binary 1, it is a plus 1 volt, and for the binary 0, it is a minus 1 volt is there. That is your BT. Then you can see there is a third one is a carrier signal. It is a carrier signal that is having high frequency. Sinusoidal signals are there of fixed amplitude. Then finally, when this would be passed through a product modulator, when the bipolar NRZ signal and the carrier signal would be mixed, and then finally you have to be generated the PSK signal, or you can say BPSK, because we are dealing with the binary symbols, the BPSK signal. So you can see the phase of the carrier would be changed according to the incoming message symbols. So when you have received the binary 1, so it would be the PSK signal will be as similar as the carrier signal, but once it would be changed its phase from binary 1 to binary 0, it would be phase shift of the 180 degree. That's why the signal would be reach this level, and then again it would be start to from the same level but from the negative to positive side. So this is nothing but a 180 degree phase shift. Similarly, when it would be goes through from the 0 to 1 again, then it is again do the same thing. Now in the positive axis, again 180 degree phase shift is there. So in this way, according to the variation of the modulating signal or the incoming binary symbols, the carrier signal would be changed its phase by 180 degrees, and then finally we have to be got a binary phase shift king signal, BPSK signals are there, or BPSK waveforms are there. So everyone please take the screenshot of this. I know this is a very less time to draw this whole, but it is a very important relationship you have to be see to represent the BPSK signal, this mathematical equation and this waveform. After that, we would be go to derive the systems hardware actually that is used to represent generate the BPSK signal. So we have to be talk about the generation of BPSK signal. So how to generate a BPSK signal? For this, whatever the hardware we have to be required, first of all, there is a binary data string that is in the terms of 1 and 0. There is no any polarity defined here. Then it would be passed through a NRZ bipolar level encoder, or NRZ level encoders are there. So it would be when it would be passed through the bipolar or polar NRZ level encoder, you would be see there is a binary symbols have been changed into the BT, that is plus 1 volt or minus 1 volt you can say, or plus A or minus A as an amplitude wise. Then this signal would be mixed up with the carrier signal, that is the mathematical representation of the carrier signal you can see here. That is square root of 2 upon TB cos 2 pi f naught t. F naught is the center of the carrier frequency. So when these two signals would be mixed on into the product modulator, and their product would be come as a out of the product modulator, that is nothing but a BPSK signal. So here the two important blocks are there: NRZ label encoder, and second one is the product modulator. So NRZ label encoder is here the input binary data sequence is encoded into the polar form with the symbols of 1 and 0 respectively, with having the amplitude of square root of ES or minus ES. You can I have represented as the energy level signals. We have already learned this, or otherwise you can say it is a uh, twice of PS minus square root of twice of PS. But both are same and both are correct. Okay. Now the second one is what the product modulator. So what is the role of product modulator is here? So product modulator which multiplies the label encoded binary wave by the sinusoidal carrier. Okay. So it is nothing but actually it is not CT, it is phi t of amplitude square root of 2 upon TB to produce the BPSK signal. So these are the